Let's talk a little bit about solar eclipses. Many of you may have seen the Great American Eclipse of 2017, where some of you saw it locally, so you didn't actually see a total eclipse, but you may have seen a partial eclipse. And in every one of my astronomy classes, I have students who actually traveled and went to a location where they could see that total solar eclipse. It's a pretty magnificent sight. So let's talk about what's happening in the heavens to give us a solar eclipse. A solar eclipse occurs when there is a new moon and it passes directly between the Earth and the sun. Okay, now new moon, does that mean we can see the moon? No, the moon is kind of obscured because it is between the Earth and the sun. And the lit side of the moon is not facing us, it's actually facing away. So when you have a solar eclipse, the moon is actually traveling around the Earth and it gets in the way of us seeing the sun. This happens very, very, very quickly. There is a bite, kind of a bite taken out of the apple, that it's kind of how it looks. And this whole process takes a few hours to get towards totality and then get out of ecliptic totality again. But how much time maximum is the total eclipse at totality? If you happen to be for this 2017 eclipse at the spot where there was maximum totality, it was only a little over 2 minutes. It wasn't a long time. And that's because the moon is orbiting the Earth at a nutty fast speed. The reason we can see the eclipse that we can is due to a very, very happy coincidence. The moon is 400 times smaller than the sun's photosphere, which is the actual disk of the sun's surface that we can see, the big yellow ball. But the sun actually is also 400 times further away. This allows us to have a perfect alignment. This perfect alignment is very, very rare, and we are very fortunate as scientists to have this situation because it has allowed us through time to see the external layers of the sun that we could not see unless it would be obscured by the moon during an eclipse. Both the moon and the sun occupy about 1/2 a degree of arc in the sky. If we go back to our measuring angles with our hands, that is about half the width of your pinky. It's not a very big fraction of the sky occupied by the moon or the sun. They look like they should take a lot more space because they're huge things, but when you look across the sky 180 degrees from horizon to horizon, only 1/2 of 1 degree is actually going to be occupied by either the sun or the moon. We are on a moving ball, and the moon is moving, of course, as well. And where the shadow falls, the moon shadow actually falls during an eclipse, is a very, very narrow band. The 2017 eclipse went from Oregon through the Midwest and Nebraska, Missouri, and then down through, I think, South Carolina in that area. On this map are some past eclipses, and then the next one that's actually going to be visible in North America is going to be 2024. So we've got a few years till that one shows up, but this one's going to have a path going from Mexico, Texas. We're still not going to see it in totality here in Wisconsin, but parts of Michigan, Ohio, and then up through the eastern seaboard are going to see that total eclipse. When you view a solar eclipse, never look at it directly with your naked eye. The sun is incredibly powerful, and the good thing is your human tendency to save yourself usually prevents people from staring at the sun because it hurts. Different ways that can be viewed. Solar glasses can be purchased for not a lot of money. When I was a little kid, my dad was a welder. And I remember, these are not pictures of me, but I found these online and thought, yep, that's a pretty good illustration. My dad used to put, his welding helmet on me whenever there'd be an eclipse so I could watch it. And that's a nice, safe way to do it. Another way is via a pinhole camera, where you basically have a card. You make a tiny little hole in it, and the rays of the sun come down, and you can focus an image on another piece of paper. How big is this? Not very big at all. I mean, we're talking small, really small, but that is one way that you can view an eclipse safely. This crazy picture is by Alex Filipinko, a noted astronomer. This is an eclipse, and I think those are 2 Tylenol or something. They made a smiley out of it, which is pretty cute. I'm going to ask you to watch a couple of videos of real eclipses in action because they're just magnificent. There are a few effects that happen very, very quickly with solar eclipse. One of them is called the diamond ring effect. When the moon is covering the sun and you get down to the point where there's one tiny little bit of the sun that kind of shows through like a diamond engagement ring, that is called the diamond ring effect. How long does that last? Moments, just very, very quick moments. The other thing that you see when the star goes to, or the eclipse goes to totality, is Bailey's beads. This was first identified, seen, named by an astronomer named Bailey. And as, again, the moon moves into position in front of the sun, it looks like a pearl necklace. It looks like little beads that you might get in a necklace. Now, what the heck is that? That is actually the sun's light passing through the valleys on the moon. The moon has peaks and valleys, and as the light streams through those, you get these areas of brightness, and the darkness are where there are moon mountains blocking the sun. That's Bailey's beads. Quite a beautiful sight. This is a picture of Bailey's beads by a Chinese photographer, Yu Zhen, and I apologize, my Chinese does not exist. And this is the diamond ring effect on this side, and then you can see the Bailey's beads over here. So beautiful time-lapse photography, and then it was smeared out slightly so you can see the changes in Bailey's beads and that change in the diamond ring effect. Last couple of slides we're going to include are starlight. You may have heard that stars twinkle and planets do not twinkle. Well, what the hey? What do we mean by twinkle? The scientific word for a twinkling star is scintillation. Okay, say that after me. Scintillation. What happens is if a star is scintillating, that means its brightness is going to change from moment to moment. What causes this? Well, this is caused basically by the atmosphere of planet Earth. The thing that you are most familiar with, perhaps, is a mirage. And I don't mean, seeing a watering hole in the middle of the desert. What I'm talking about is maybe on a hot day, you are driving down a hot, flat piece of pavement, and you see what looks like kind of a Ripley effect, because heat is rising off of the distant road, and it all kind of looks shimmery. Well, hot air has a tendency to rise, cold air has a tendency to fall, and what that means is there's a lot of motion in the atmosphere of planet Earth. Astronomers who are looking up at the stars from planet Earth actually have to look through this crazy, wiggly, moving atmosphere. And it makes the light from the stars appear to change their brightness from moment to moment or twinkle. And it all has to do with our atmosphere and heat. Now, the concept that stars twinkle and planets don't isn't 100% true, but there is some validity to it, and here's why. Stars are so far away that they look like individual tiny little points of light in the sky. And so one little bit of starlight can wiggle a little bit as it goes through the Earth's atmosphere. Planets are so much bigger because they're so much closer. They don't reflect just one little point of light. A planet actually looks to us, even through telescopes in our naked eye. It's not just reflecting one little beam of light, but multiple beams of light. And as that light goes through the Earth's atmosphere and all of the crazy heat motions that make light kind of twinkle or scintillate, some of them might be twinkling in one direction, some might be twinkling in another direction, but we are getting so many more beams of light that they kind of cancel out, and this looks like a disk in the sky. So there is a lot less twinkling, a lot less scintillation when you're talking about a planet than you're talking about a star. And that's just due to lots of beams of light increase the clarity of the image that we are looking at. There's a little video I'm going to ask you to watch. That will end this whole section. See you later.